Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is the vector nature of forces. And at this point in the course, we're going to start looking at motion in a slightly different way than we have up till now. If you think of the kinematics unit, where we talked about displacement, position, velocity, speed, acceleration, and whatnot, we talked about motion, but all we did was really describe what was happening to an object, like how fast it was going, how far it was going, where it was moving to. We never really discussed why it was doing the things that it was doing. That's what we're going to start talking about now with discussion of something called forces. So if you've wanted to answer the question of why do things behave the way they do, you have to look at motion from this point of view. So I think you'll find this an interesting topic, to say the least. Take a moment now to pause the video and have a look at the first screen here so you see the kind of questions that we're going to answer in today's video, as well as where we are in the unit schedule, and also what are the learning goals and success criteria. Okay, and you're back. We're going to dive right into things here. We're going to go on to our first screen. I've got a whole bunch of pictures here. I'd like you to take a look at them. The first few deal with a force that you are very familiar with. This one over here, we all recognize this image. It's an image of an astronaut near the space station, and this astronaut is, along with the space station, orbiting Earth. What is the force that is allowing the astronaut and the space station to orbit Earth? I think we all know that that, of course, is the force of gravity. Gravity is a force that attracts objects in the universe, and right here the Earth is attracting the astronaut, causing the orbit. What might not be so obvious is that the astronaut and the space station are also attracting Earth at the same time. That's very difficult to observe because the Earth is so much more massive than they are. However, as we get into this unit, you'll learn that that is in fact one of the rules or laws that forces follow, and I think it'll help you to explain a lot of the examples of motion that you see every day around you. Let's take a look at another one. Here you see an airplane that is either coming in for a landing or maybe about to take off. The force of gravity, of course, holds this airliner down onto the ground, so we can also say that gravity is acting here. You don't have to be out in space for gravity to be a force. Of course, getting back to the space theme on an even larger scale than what you saw over here with the space station, take a look over here. This is a artist conception, roughly to scale, of all of the planets and some comets as well, and the asteroids that are orbiting the sun. And if you look at this, you'll see once again it's not obvious that gravity is the force that's leading to these orbits. But if gravity is the force up here that can cause an astronaut and a space station to orbit Earth, maybe that's also the force that can cause the planets and the asteroids and the comets to orbit the sun. So gravity is certainly a very predominant force in our lives. What are some others? Well, take a look at this picture here, a whole bunch of balloons that are kind of sticking against the wall. If you've ever been to a children's party, maybe you saw people rubbing balloons in their hair and then sticking them up against a wall, and they somehow stick magically. What is the force that's allowing them to defy gravity and stick to the wall? Well, this time it's got something to do with electric charge, because if you rub that balloon in your hair long enough, you feel little sparks. This is what we call the electric charge, or more correctly, the electromagnetic. See if I spelled that right. Electromagnetic force. And this is the force that allows opposite charges to attract and exert some sort of force, and therefore keep the balloons stuck to the wall. In the word electromagnetic, of course, you hear the word magnet, and the force that allows the balloons to stick to the wall is actually the same force that you've experienced when you were a kid playing with magnets. Like poles repel one another, so two souths or two norths, but opposites attract, so a south and a north like this. It's kind of the same idea as the electric force, where electric charges that are opposite are attracting, and if they are likes, they repel. So for example, positive to positive will repel, negative to negative will repel, but positive and negative attract. Same sort of idea with magnets, only with north and south poles. Here are some other examples. Here we see a crane that's lifting up a load off of a container ship. And of course you can guess that gravity, sorry, I'll draw that a little bit easier for you to see. Gravity is a force pulling down, but if there's a force pulling down and we're still managing to lift this load, then there must be some force counteracting it. It's the chains, of course, here. But what is the force in these chains? We have a name for it. We call it tension. So tension is an example of a force that you'll encounter on a fairly regular basis. Tension in a string, tension in a chain. Let's go back up here to a picture of someone who is striking a match on a matchbook, trying to light it. Here there's a number of forces. For one thing, the person is applying a force, and we might call that the applied force. The person uses his or her fingers to do that. But there's also a lot of rubbing and heat that goes on here. And the force that we're talking about here is friction. In fact, this friction is what's going to actually light the match. Looking a little bit further down, we see a car that is apparently skidding off the track. It's in a race. What is the force there when you're skidding? Once again, of course, that is friction. So this is a very common incident where a car may be skidding, or maybe you're running and you go sliding for whatever reason. You're trying to stop suddenly. So friction, also very common. Let's take a look at another example that, of course, is very important in our lives, but we don't really see it every day, and that is the structure of the atom. A lot of you will recognize this image here. Looks like maybe a Bohr-Rutherford diagram that we might see in grade 9, where the electrons are in orbitals or energy levels orbiting the nucleus. And of course, in here, where we have the nucleus, there are no electrons in the nucleus. There are the protons, and of course there are in all but the most basic atom, hydrogen number 1, there are neutrons. Now think back to what you learned about neutrons and protons. Neutrons, of course, have zero charge. They are neutral, hence their name, but protons are positively charged. Now, have you ever wondered, why does the nucleus stay together? After all, we just learned in these two images over here that like charges or like poles will repel one another. Why aren't the protons repelling one another in nucleus? Why does the nucleus stay together at all? If you answered because of the neutrons, then you might be right, depending on why you answered. Did you answer because you think that neutral charges, neutrons, attract protons? Well, they don't really. The rule is that opposite charges attract protons and electrons. So if that was the reason for answering, then sorry, but you were kind of wrong. On the other hand, it is true that neutrons provide some sort of stabilizing force inside the nucleus. There's a lot of repulsion between the protons here, and something is holding them together. It's partly the neutrons, but it's also something called the strong nuclear force. This is a force so strong that it's able to overcome the repulsion of positively charged protons. There's one other force that you're probably not really familiar with, and it is described in this diagram here, which you may or may not recognize. We have another nucleus, and out of this nucleus is flying a particle which is labeled with the Greek letter beta and a minus sign beside it. So what is this referring to? This is a sort of what we call radioactive decay, where a nucleus can actually emit particles in what we call radiation. In this type of decay, what happens is one of the neutrons, symbolized by the letter N, actually mutates into a proton, symbolized by the letter P. And of course, if you lose a neutron and gain a proton in the nucleus, by gaining a proton, you've changed the actual element. It has mutated into a new form. And so this procedure, called beta minus decay, is a method by which some atoms can mutate into different forms. However, what's interesting is a neutron with zero charge, neutral, suddenly gives birth to a proton with positive charge. And you might be wondering, where does positive charge come from here? We started with zero charge. How did we get positive? Well, the answer in part is that a negatively charged beta particle, which is actually just an electron, gets spat out of the nucleus. So in the end, zero charge to begin with leads to positive and negative charge, overall zero, and therefore this procedure is possible. It doesn't violate the law of conservation of charge, but it does allow a mechanism for what are called radioactive atoms to mutate into a new form. Now, when they do this, there's a special force which is only in the nucleus, and this one's called the weak nuclear force. It is responsible for this kind of behavior of certain atoms, and it's certainly a very interesting process, radioactive decay. I encourage you to look into it if you want to learn something interesting about nature. But there we have it. There are 4 kinds of forces: gravity, electric or electromagnetic, the strong nuclear force, and the weak nuclear force, plus a few others, which are called, for example, tension, or maybe friction, or maybe an applied force. We're going to be looking at these in a lot of detail in this course. Let's switch to the next slide now. And actually, here's the fact of the video. Believe it or not, out of all of these forces that we talked about back here, there are actually only 4 basic ones. Of those 4, let me list them for you. The 4 forces that are very basic, or what we call fundamental, are gravity, the electromagnetic, the other ones are the nuclear forces, the strong nuclear, and the weak nuclear. Now let me try to explain by going back here for a moment. What did we look at here? We looked at, for example, friction. Why does friction occur when 2 objects slide past one another? If you think about it, it's because there's some sort of interaction between the surfaces of the 2 objects. If you could somehow zoom in really close, which I'm going to try to do right now, maybe imagine zooming in to the point that you could actually see the atoms in the surface of the match and the surface of the matchbook right here. What would you find? You'd find atoms that, of course, are attracting one another. And this leads to a force that we call friction, but really it's a force that's caused by the fact that atoms attract one another, and this is nothing more than the electromagnetic force. So friction is actually part of the electromagnetic force. Friction's not a new force, it's just one example of this. For that matter, the applied force, when you touch the match and push it, the same sort of thing is going on. Your fingers are touching the match. Fingers and skin, the atoms and molecules in there, are touching wood. The same sort of thing that allows the friction to occur in the first place is occurring in this situation. Once again, it's electromagnetic. Here's another one, tension. What allows the chain to pull up the load that we see over here? Well, it's the strength of the chain, but what is that really? Once again, imagine zooming in so that you could actually see on an atomic scale the links in this chain. What would you find? You'd find atoms attracting one another. And so really, what is the tension force? It's nothing more or less than an example of the electromagnetic force. So even tension is electromagnetic in nature. There was one other force that I didn't mention. I'd like to go back to the airplane to talk about it. The airplane is pulled down by gravity. As we all know, airplanes are very heavy. And they sit on the runway. The runway supports them. So the runway is exerting a sort of force upward. You might call this the surface force or the support force. But we have a name for it. It's called the normal force. And you might be wondering, why is it called the normal force? That's not because other forces are abnormal. It's because in mathematics, the word normal refers to 90 degrees. And the normal force, if you see, is perpendicular. It's 90 degrees to the surface, the runway here. So the normal force, once again, which is the support given by the runway to the airplane, that's because the runway is strong. The atoms and molecules within it hold together and hold up the airplane. It, therefore, is also an example of the electromagnetic force. So getting back to this slide here, virtually all the forces you encounter on a daily basis are electromagnetic. Many, of course, well, only one kind can be gravity. That's what holds you down. The nuclear forces are hard to see on a daily basis. They only exist within the nucleus of an atom. However, Believe it or not, physicists have been able to explain all forces in the universe just by using these four categories. Everything falls into one of these four categories. So now let's talk about how forces are measured. The unit of measurement for forces is named after Sir Isaac Newton, and it is called the Newton. The symbol is N. So for example, pick up your smartphone if you have one right now. If you pick up your smartphone which maybe has a mass of, I don't know, maybe it's something like 200 grams. What is the force acting on this, the force of gravity? Well, it's approximately 2 newtons of force in the downward direction. Pick up your textbook. Your physics textbook might have a mass of 2 kilograms, roughly 10 times your smartphone. Gravity once again pulls down on that with a force of approximately 20 newtons. And right now, if you are standing next to a friend of yours, and your friend will let you do this, pick up your friend. Your friend may have a mass of 65 kilograms. The force you will have to exert to overcome the gravity on a 65 kilogram person is approximately 650 newtons. These, of course, are all down in the case of gravity, although if you want to lift your friend up, then you've got to exert the force up. But the reason I'm pointing out these numbers is to give you an idea of what a few newtons feels like. Think of picking up your cell phone. What does 20 newtons of force feel like? Think of picking up your textbook. What does hundreds of newtons feel like? Think of picking up a person and the force you'd have to exert. All right, so what do forces have to do with vectors? Well, it's pretty clear that forces have magnitude. There's an amount to explain them. But you also have to exert them in a certain direction. Like you have to exert a force upward to lift your cell phone, your textbook, or the person. And if we go back to some of these pictures, for an airplane to take off, it's got to exert a force up, but gravity is exerting a force down. The plane has to push itself forward with its engines, and there may be some air resistance pushing it backwards. This car here is trying to go forward, as you can see, going this way. Its engine exerts that force, even as gravity pulls down and the road supports the car and pulls up, and there's even some friction going backward. So forces can act in many different directions, and that's why we have this, the direction. So what you'll see is something like F, the symbol for force, with a vector hat, and you might see something like 20 newtons, and then square brackets, maybe down, or whatever the direction may be. So guess what? We're going to revisit vectors like we did in the previous unit on kinematics. Let's move on. When we're analyzing forces, we draw a special kind of diagram. It's called a free body diagram. Here's an F1 racing car that is clearly going forward. The driver gets the engine to apply a force forward. We might call that an applied force. Maybe we would call it the engine force. Who knows? There's a lot of wind when you're riding in one of these cars. There's going to be some friction pointing backwards. Of course, this car is not light. The force of gravity will pull it down to the ground. And of course, the road will support the car, so there is an upward force, which once again we call the normal, or Fn. So there are 4 forces acting on this object. Here's what we do when we're drawing this as a diagram in a solution. We simply draw the car as a dot, and we draw each force vector coming off of that dot in the direction that it's going. We try to draw the force vectors roughly as long as they would be in relation to one another. So, for example, the normal force is balanced by gravity. We know this is true because the car is not flying up into the air and it's not sinking down into the ground. So we might indicate these the way they do in math class with a couple of tick marks to show that the lengths are equal. On the other hand, the applied force from the engine is probably going to be greater than the friction force exerted by the wind and the road. We know this because if the car is speeding up, there's got to be some extra force going forward. So now I would not put tick marks like that, because these forces are likely not going to be the same. Now, once we know all the forces acting on an object, we calculate what's called the net force. The way you calculate the net force is you got to think, what does the word net mean? Well, as in business, where it means add up all the forces, what we're going to do here is the following. We're going to write F net equals, and then we're going to list all the forces here. So F applied plus F normal plus Fg plus Ff. Now, I haven't given you any numbers here, so maybe we could make some up. What might be the gravity force on this car? Well, I'm going to take a wild guess. I don't know F1 racing too well, but I'm going to go with, I don't know, maybe 5,000 newtons. I could be off. I encourage you to look this up and correct me if I'm wrong. As we said, the normal and gravity have the same magnitude, so I'm going to write 5,000 newtons here. I'm not going to write up because the arrow shows up, and here the arrow shows down. What might be the applied force? Again, I don't know how much force these engines can put out. I'm going to take a wild guess here of 10,000 newtons. Maybe in class I'll explain to you where I came up with these numbers. For the friction force, I'm going to say, I don't know, maybe 2,000 newtons. So whether or not these numbers are right, we can still use them to calculate what's called the net force. Here's what we do next. We write in each of these 10,000 newtons to the forward direction. The normal force is 5,000 newtons up. The gravity force is 5,000 newtons down. And the friction force is 2,000 newtons back. Now, you can start thinking of your vectors here. For example, it's pretty clear that 5,000 newtons up and 5,000 newtons down will cancel. That's because a down is the same as an up if you put in a negative there. So we've got 5,000 newtons up and negative 5,000 newtons up. They cancel. Let's take a look at this one. 10,000 forward. Here's a back, which is the same as a forward if we put in a negative sign there. So now we have 10,000 newtons forward minus 2,000 newtons forward. All that leaves me with is 8,000 newtons forward, everything else having canceled. And that is what we call the net force. It's the overall force once everything is taken into account. Let's finish up now with a couple of instances that you're going to encounter. There's something called collinear forces and non-collinear forces. As the name suggests, linear means in a line, and co means the same. So collinear forces are forces in the same line. Here's a sprinter, and the sprinter is clearly exerting a force forward, which I'll try to show here in a color that you can see. The sprinter is exerting a force forward. Of course, there's a little bit of wind resistance going backward, so I'll draw that in. The sprinter is also experiencing the normal force as the ground holds him up, and the gravity force as gravity pulls down. Now, if you look at these forces, the blue forces are in the same line. Forces are also in the same line. Very much like we had in this example here of the car. These forces are easy to add and subtract. The ups and the downs cancel, the forwards and the backwards cancel. Enough said. Sometimes the forces are not in the same line. Look at this situation here in the game of football, where the two guys in the white shirts are trying to tackle the guy in the blue shirt. If we look at this situation from a bird's eye view, if we look at this from a bird's eye view, what might you see? Now I'm guessing here, but I think you would see something like this. This guy here is going forward, so let's designate some directions here. From a bird's eye view, I'm going to call this the forward direction, sort of towards us, and here's the back direction. And then we've got someone to their left, the blue guy's left, but we could call that our right. And then, of course, we've got the direction that would look this way, our left. Okay, now think about this guy, number 9, it looks like. He's pushing, it looks almost sideways. So I'm going to put in that number 9 has a force that is going this way. Of course, remember, the guy getting tackled is drawn as a dot at the center. So he's getting a push this way from number 9 over here. But what's this guy here? I don't know if that looks like an 8 or something. Number 8 is pushing to the right, but it looks to me like he's also pushing backward a little bit. So I'm going to draw a force that's a little bit back and to our right, like this. Meanwhile, number 81 here is not going to, he's not going to stop running. Number 81 here is going to keep running with his feet. He's going to keep pushing forward. So he's got a force on himself going in this direction. What do you notice about these three forces? They aren't all in a line the way the forces were with the runner here or with the drag race or the F1 racing car. So what do we have here? We have both in the same line, non-collinear forces. How do we add these forces? Well, you guessed it, folks. It's back to two-dimensional vector addition. I know you know how to do this because you did it in the last chapter. I'll write in here, recall when we did displacement. We used to add up various different forces. We would say something like, Billy walks this way, then that way, and then this way. What is his displacement? And you'd have to say, oh, that's from the start to finish. Voila. Well, the same way you saw this with displacement vectors, now you're going to take these and add them together in order to get what's called the net force. Lots of questions to try in the textbook, sample problems given. We're going to meet up in class and try a bunch of these, but now at least you have an introduction to what you have to do. You got to add these forces. You're going to have to take these three. I'll create some room here by just deleting this to give you a rough idea of how you would proceed in the football example here. You would take the first force, and you would add tip to tail this force, and then you would take this force, which looks like it's kind of going that way, and your net force would go from the very beginning to the very end. This is what we would call F net when adding non-collinear forces. These other forces, of course, would be, what did we say? This was the force by player number 9. I'll call that F9. This is the force by player 8. I'll call that F8. And this was the force by player number 81. So that maybe I'll call it F81. Well, you would add these up in here. F81, F9, and F8. And you guys know how to deal with this. Scale diagrams or trig will allow you to solve. All right, folks, thanks for watching. Lots of questions to try in the book, in the homework schedule. I'll see you in class. Have a good day.